Hello everyone, it's Nono here, and I want to welcome you to the Nono.MA live stream. This is a slot of time that I reserve every week to play with creative coding, machine learning, and other stuff. Thanks for joining. If you're new, I'm Nono Martinez Alonso, and if not, welcome back. So let's get started. Today, I want to get back into doing exercises from the machine learning book that I've shown on previous lives. So let's get into it. First reminder, your likes support the channel and the work that I'm doing here. And if you want to get notified, you can subscribe. When I go live or when I post new videos, you'll get a notification. And you can join us on the Discord server. The community keeps growing. You have a QR code there, or just go to this invite link at Nono.MA/Discord that I'm going to paste on the YouTube chat as well. So Nono.MA/Discord. And yeah, so without further ado, we're gonna get started. This is not last week, it's 2 weeks ago. We took a look at more classification work with TensorFlow.js. We didn't get to the AI drawing part yet, but we've done a lot of groundwork and edited a lot of the tutorials that you can find on YouTube already. If you're connecting live, I will be thankful if you were to post a message saying that you can see me, that you can hear me okay. And today we might have to do a short live stream. Also next week, I'm gonna be probably out, so I won't be live streaming. All right, so an announcement. So at the end of May, we published a new episode with Hector Ruiz, Magic and the Art of Illusion. Illusionist Hector Ruiz on getting started and standing out as a magician, how COVID-19 changed his world, his take on talent, effort, creativity, success, and entrepreneurship, and more. I have really quickly, maybe I can show you here. Okay, hello, Jose Luis. Nice to see you around. I see that Jose Luis has the notifications turned on because he was right in after we connected. And let me see. And Jose Luis is putting a goggles icon because the reason why I won't be live streaming next week is because we're gonna do a free diving course and I'll be going with him. So let's see, maybe we can tell you a few things about that. Actually, for those of you who don't know it, I posted a post with this weird instrument that we're using on the free diving course and some thoughts if you want to see sketch.nono.ma. And I was talking about Hector Ruiz's episode, right? As always, you can listen on Apple Podcasts, Spotify, or YouTube, but this time on YouTube, and you might hear some of the audio.
With two main goals: a magic effect, like what you see as
you
an
can
audience,
also see
a magic effect
Hector
using a
and
secret
myself
that didn't exist before. So
exchanging words over Zoom. So I
this idea that I
tend
had
to
2 years
prefer
ago, and maybe
doing
6
these
months later,
things,
I read a poem and
I tend to prefer doing these things recording in person, but because of COVID and many other things, this is not that easy. I won't show anything now, but I'll show in the future that we're going to release full video interview with Luis Ruiz and a teaser in the short term. It's already on YouTube. We just need to publish it and see how we share it. Okay, keep going. You can connect with me or submit questions about past podcast episodes at gettingsimple.com/ask. And let's get started with today. So this is what we did last week. Today, I'm going to try to cover an introduction to Autoencoders. So in case we get something out of this, I'm going to make an intro screen. Hi everyone, it's Nono here, and this is an overview on how to use autoencoders with Keras and TensorFlow, and hopefully we get to see the TSNE, or however that's pronounced, algorithm as well. We're going to be following a few pages of the Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow book. There is a short URL there, Nono.MA/HOML or HOML for Hands-on Machine Learning. It's a sponsored Amazon link, but you know, it's okay. You can just look for the book on Amazon and go to it. It's I don't know if you'll see it there, but you know, it's this book that is been awesome for me to learn and deep dive into machine learning concepts and also hands-on coding. All right, I don't have the best slides today, but you know, I just took a picture of the book, so this is like a few pages of the book scanned for me to show here, and the link and the reference there. Chapter 17, already in page, I think 567, covers representation learning and generative learning using autoencoders and GANs, which is generative adversarial networks. Autoencoders are artificial networks capable of learning dense representations of the input data, called latent representations or codings, without any supervision. Kind of going back a bit, we've been doing some hands-on programming with TensorFlow JS and Pix2Pix and other models, and converting TensorFlow models and things like that. There is also a bunch of tutorials with Runway ML and Lobe and many different things. But one of the main interests that I had, that is how I started the channel, was to deep dive into actual hands-on coding of new machine learning concepts that I haven't tried, right? So today's live stream is going to be about trying to write an autoencoder. Just type the code that comes on the book and try to understand it a bit, try to see how it works. And here we can see all right, so one quick second and I'll be, let me just put this thing here, 1 second. Glad that we had Jose Luis here today with us. So I just realized, let's divert as I may, as I like all the time. So I just saw Jose Luis realized that I've been posting to a Discord channel all the updates on when we were going live that doesn't really exist for other people. I didn't know that the visibility was not okay. So thanks for that. Let's try to go into that really quickly and at least let everyone else know on the live chat. I think this should be, yeah, so people can write here. I have been posting here, and this has been always for myself. I don't know why. Greyfish, some people could see this one. So yeah, if anyone's online, I would really, I don't know who. Yeah, I'm really not sure why Jose Luis cannot see this channel. So you guys let me know if you can access this now. I'll edit this category: permissions, view channel, manage channel. All right, great. I'm glad that this is working. So I'll say here, not the history, okay. Hi everyone. we're live right now. All right, so we'll try this. I don't know exactly how Discord works, but yeah, I'll just put that there, and hopefully everyone can get these messages from now on. I'll put the link again in case somebody didn't get it. Cool. All right, you learn something every day. And I'm going to close this for performance, but you guys tell me on the video chat if you could see that. All right, so let's get back here. So this, and thanks Jose Luis for this. Gracias. All right, autoencoders. These codings typically have much lower dimensionality than the input data, making autoencoders useful for dimensionality reduction, like you can see in chapter 8. Especially for visualization purposes, autoencoders act as feature detectors, and they can be used for unsupervised pre-training of deep neural networks. As we discussed in chapter 11, lastly, some autoencoders are generative models. They are capable of randomly generating new data that looks very similar to the training data. For example, you could train an autoencoder on pictures of faces, and it will then be able to generate new faces. However, the generated images are usually fuzzy. All right, between you and the video. All right, I don't know what's going on today. 1 second. Okay, I'm just trying to make sure that everything is working properly as always. Okay, so what we're trying to do here is just to recap in case that this doesn't make any sense. Usually when you have a bunch of data, so your data set in this case is a raster pixel data set, it's hard for the models, for a model to make sense or to reduce the dimensions of that data, right? That's like to classify types or to recognize features or things like that. And when we have an autoencoder, what it does is that it creates some latent representations or codings of your data that have less dimensions than the original data set, right? And that helps us use that data, so those codings of the data set, as reduced dimension codings that we can then maybe flatten into a 2D space with the TSNE algorithm, right? This might not make a lot of sense. It does for me, but I'm also trying to learn here. And what I mean with TSNE is this algorithm that allows us to reduce a data set. In this case, this is the fashion eminence data set we've seen in other live stream videos, into a 2D space by similarity. So, right, so this creates a latent space or like a flattened visualization where we can see, for example, all of the shoes are clustered along the same place. The longer boot are here, like mid boot and then low boot, or low ankle, and then sandals, right? So, and you can see actually what the book says is that the scatter plot actually matches the classes reasonably well. That means that you can see here that each color represents a class, and except for a few classes that are confused, like different types of shirts and t-shirts, others are pretty well isolated. For example, like all the trousers are here, all the things that have to do with dresses and shirts are here. These are all the bags. This is the sandals and all the shoes, and then shoe types. and the output of an autoencoder, right? So this would be the output, and this would be the images, that the reconstructions that the autoencoder learns to generate later. They're faster, but they look a lot alike the input images. All right. So there is this concept of stacked autoencoders or deep autoencoders. Just like any other neural network we have discussed, autoencoders can have multiple hidden layers. In this case, they're called stacked autoencoders. And adding more layers help the autoencoder learn more complex codings. That said, one must be careful not to make the autoencoder too powerful. Imagine an encoder so powerful that it just learns to map each input to a single arbitrary number, and the decoder learns the reverse mapping. Obviously, such an autoencoder would reconstruct the training data perfectly, but it won't have learned any useful data representation in the process, and it is unlikely to generalize well to new instances. What this means is that you can overfeed a model. If you make it too deep, it's going to learn everything on your data set, but it will only be able to generate data that looks exactly like the samples that you have, and that's a bit useless. What you want is your model to be learning a lot, but be as simple as possible for it to be able to learn features faster and then generalize to new data samples that it hasn't probably seen in the future, like new instances. The architecture, so let me see. All right. The architecture of a stacked autoencoder is typically symmetrical with regard to the central hidden layer, the coding layer. To put it simply, it looks like a sandwich. For example, an autoencoder for MNIST, introduced in chapter 3. And this is not MNIST, the MNIST of Jan LeCun with numbers. It's fashion MNIST, which is a data set that contains fashion clothing, analog to the MNIST machine learning dataset, but made by Zalando, and I think they're also 28 by 28 pixels. So Zalando 28 pixels. Let's see if we find that. Yeah, so Zalando, which is the Amazon for clothing or something like that, it's like has this made this dataset of 60,000 training images and 10,000 test set images. That contains 10 classes of clothing, and those are the 10 classes that we can see in here, right? So we can see 10 clusters, different clusters. And if we go back to where we were before, for each example, an autoencoder for MNIST may have 784 inputs, followed by a hidden layer with 100 neurons, then a central hidden layer for 30 neurons, then another hidden layer for 100 neurons, and an output layer with 784 neurons. This stacked autoencoder is represented in figure 17.3, right? So we have here our output is the image, so it's 28 by 28, right? It should be just 28 by 28, 784 pixels, or yeah, like individual pixels. 100 units, a hidden layer, then hidden, and output layers. And the codings are written here. I think this is basically a feature detector. We'll take a look at that. Don't take my word. Implementing a stacked autoencoder using Keras. You can implement a stacked autoencoder very much like a regular deep MLP. In particular, the same techniques we use in chapter 11 for training deep nets can be applied. For example, the following code builds a stacked autoencoder for fashion MNIST, loaded and normalized as in chapter 10 using the CELU activation function. So instead of ReLU, we use CELU. So we're going to look here for machine learning CELU. All right. Let's see. So I'm not sure. I'm going to open Discord again just to see if people got the notification or not. CELU. Meet CELU. All right. So CELU is slightly different than ReLU. Looks pretty similar to Leaky ReLU, but wait to see its magic. All right. So maybe we can try to understand this in a future video. Right, so CELU and ReLU are activation functions. This is how the activation graph looks like. And if you look for activation functions, you can see some of the others. It looks similar to, so where is Leaky Rel? So it's similar to this one, but it has a curve, so like this one, right? All right, Jose Luis can see things now. And that's cool. Great. All right, so let's start writing code here. So we have this thing. So this is the code. We have the stacked autoencoder and the decoder. This is what we can see here, I believe. Dense 100. Yeah, so this is exactly what we're seeing there. Okay, we're just gonna test this code. This is what we're gonna do, and I'm gonna have to stop in a few minutes and come back. All right, so let's open, pause here. Cool. So again, I like to use Colab in this video series, and that's what we're gonna do now. I was taking a look at the autoencoders and GANs I think last week, and there is some code here for what we're gonna do. We actually have probably the same code here, stacked autoencoders, and okay, well, we'll take a look at, oh, you probably cannot see anything. We'll take a look at all of this. Yeah, so this is what we're gonna try to do. Okay, so new notebook. We'll put the date on the name and the live stream number. And again, if you're connecting live, tell us where you're connecting from, if you can see me well, and what you're looking forward to learning from this channel. All right, so we have here stacked autoencoders, and this is live 33, maybe like that. Okay, so first import TensorFlow. So I think we can directly import Keras from TensorFlow. Yeah, we've jumped a bit from MLPs. Let me just take a look here at the book. So this says here, autoencoders simply learn to copy their inputs to their outputs. This may sound like a trivial task, but we will see that constraining the network in various ways can make it rather difficult. For example, you can limit the size of the latent representations, or you can add noise to the inputs and train the network to recover the original inputs. These constraints prevent the autoencoder from trivially copying the inputs directly to the outputs, which forces it to learn efficient ways of representing the data. In short, the codings are byproducts of the autoencoder learning the identity function under some constraints. So the coding are byproducts of the autoencoder learning the identity function under some constraints. All right. So efficient data representations. Cool. So here, all right, let's take a look at this diagram here before we get started. Okay. Cool. So all right, so here you can see latent representation. So you have a representation for each input in the model after the encoder has finished, and then the decoder tries to generate the same image, right? That's why this says outputs are more or less the inputs, right? So you have 3 inputs, and then you have x1, x2, x3, which in the input image would be our 768 pixels, and the outputs are sort of that, right? Like what we're trying to do is for the model to reconstruct those. And here, performing PCA with an encoder under complete linear autoencoder. Right, to codings predict. Okay, let's go and try to do this coding exercise. So we have here so just to make it clear, I always like to do import TensorFlow as TF instead of importing just Keras, but you can do whatever you prefer. All right, so I have here my image. And we have here TF Keras. So let me make this big. All right, so we're going to define 2 variables here as we saw before in the code. So the stacked encoder and later the stacked decoder. And once we have those, which each of those is going to be a TF Keras model's sequential, each of them is going to be a sequential model. I don't think we can do this without the code failing because we need layers, but let's try to run it. All right, so let's try to run this here and this here. All right, it runs. So let's see a stacked encoder. Yeah, we just get a stacked decoder, an empty sequential model. All right, so we'll have 2 different sequential models. So those are 2 Keras models. We've seen this on previous live streams. And now you will have the stacked autoencoder. So it says here, but autoencoder. I just like to make variable names long so it's legible. TF Keras models, sequential. And we're going to actually stack them. So we're going to put here first the stacked encoder and then the stacked decoder. And I don't think we need to make this so deep. All right, right, so we have those 2, and that would be our network, right? So we'll just have the these 2 kind of blocks or sub networks. We'll have them here into a bigger autoencoder network. And again, this is an autoencoder, so we can post it here, and is cannot be used as a layer. All right, yeah, so this is the error I was getting around before, right? If these models are empty, we cannot use them as layers because the input and the output of each layer cannot be determined, but this code will work later. Here we have then to compile, so we will get our stacked autoencoder and we'll compile it with set of parameters. So we'll have a loss and an optimizer, which we have to put here. And we'll take a look, or we'll train the model looking at the history. Stacked autoencoder, we'll do fit, and then we'll pass our train data, our I wonder if this is like a typo or this is okay. It says X train. All right. Epochs 10 validation data X valid, and we need to load the data. We don't really have that data right now, but we'll see how to load the MNIST data set. All right. So what time is it? Okay. All right. Well, we've done that in previous live streams. I'm not sure if I'm going to be able to find that right now. Maybe it's even easier just to look for, well, maybe it's here. Oh, here we go. All right. This is how we can do it. Okay. Cool. So we can get to that here. So this is just TF Keras, okay, fashion MNIST. So let's put here a new category that's going to be load dataset. This is a fashion MNIST dataset. And a blog, and now here define autoencoder. All right, so we'll do here TF Keras, is it data? Datasets, fashion MNIST, load data. All right, so let's see these downloads from Google's repository, and we have all the data here. And now we can deconstruct this variable into X train full and Y train full. So this would be X train full and Y train full. All right, so now if we do X train full, shape, oop. All right. Okay. And X train full as type. So this is a remapping. Let's understand this code here. So we're casting to float 32 and dividing by 255 to get the values of the pixels colors from 0 to 255 to 0 to 1, and the same for the test data set. We're not even loading the test data set here, and that's going to give us an error. All right. Okay, there might be something here. Okay, so I got that. Okay, that makes sense. So let's see if we can actually do what I tried to do before. All right, so we have 60,000 28 by 28 images, and these are the outputs. So these are the output for each sample. And then here we have the X test, which will be 10,000, and Y test that will be 10,000 as well. These are images and outputs, If we print that, we just get the classes. So this is actually encoding each image into a class, right? So we get the input is an image and the output is a class. and that's for training the encoder. All right, so we're going to just get all of this information, so we get all of the X train is valid. All right, and MP is not defined. All right, import NumPy as MP, so we load the NumPy library. We're going to remove this cell, load that, and then do that. Cool. So now we have our data, and then we can get started or continue with where we were before. I'm to understand this part here, the X train, X valid, but we'll see that when you get there. All right, so layers on our stacked encoder. So we have here, this is the encoder, so 3 layers here and 2 for the decoder. All right. Great. And those 3 layers are TensorFlow Keras layers, flatten. Our input size is 28 by 28. Then we have a dense layer with 100 units. Activation, as we saw before, is Celu. And we're going to do the same for the last layer, but with 30 units. And that's our encoder. And then for the decoder, we have here TF Keras layers dense 100, activation, apps equals Celu. The input shape now is an encoding that is actually 30 digits. Then we have layers dense 28 by 28. The activation is sigmoid, and lastly we have a reshape. So whatever we get from there, we reshape it into an image, and that's it. And we have our decoder. So now that we saw this, this makes a bit more sense to me, because what we're doing here on the encoder is that we're going from a 28 by 28 pixel image into a 30 digit or 30 unit coding or encoding, right? So that's a coding, and then that is what this decoder gets, that 30. We get that 30 back to the input shape of this one, and then back into this shape we get like a linear unit of 768 digits, and then we reshape that into a 28 by 28 pixel image. That is why, you know, it didn't make sense to me before, but it does now. So let's see. An empty model cannot be used as a layer. And empty model. All right, so let's see why this. So we run these two. Okay, there's an error here. Input shape. Right, so I'm gonna have to stop for a second really soon, but let's keep going. So we have the encoder and the decoder, and now we compile the autoencoder. It does make sense to me now that we're inputting X train, which is a, you know, if we get X train here and we do X train shape, we have 55,000 images that are 28 by 28 pixels, and that's the input to our encoder in the autoencoder. And then this gets to 30, but then gets into 30 here and gets out as 28 by 28 at the other end, right? So with that said, now we have a thing here that we're going to train, and it makes sense because we want the input to match the output, and we're just training for 10 epochs, and this is the validation, which is so if we do 5 divided 60, right? So it's 8% of our data is validation, and the rest 92 or 91% is training data. So here for the loss, we're going to use a binary cross entropy. We're going to ignore what that means right now. And we're going to use a TF Keras SDG stochastic gradient descent, I think, for our optimizer, right? So we have that, and I think we have everything now. So we have our model. LR is deprecated, and I like that. Learning rate. I like these things because LR might be good for people who know already a library, but learning rate will make sense to anyone who knows machine learning, and or doesn't. You can go and look for that concept now. So on this history, when we execute, we're going to train for 10 epochs. Hopefully that works, right? And this is messaging that shows up on TensorFlow normally. And you can see right now something's wrong, but that wasn't too fast. So here's the moment where I have to go for a second. All right, I'm gonna take a 5 or 10 minute break, and we'll be back. So I'll leave this online for now, and I'll see you soon, and we'll continue for a bit. Hello, we're back. Hello, Rob. Nice to see you around. And yeah, so we had a long break. So we're gonna get back now at what we were doing. Where were we? All right, so we got an error here. As a quick recap, we were taking a look at how to build an autoencoder. This is a network that tries to create codings for input images in this case, and tries to reconstruct them later. So it tries to learn how to code an image and then decode it back into an image. And an example we saw here is that in this particular algorithm, we get these inputs and then the network learns how to reconstruct them from here. As far as I understand, what's going on is like, an image has 768 pixels, but that's actually, well, in this case is black and is grayscale, so it's from 0 to 255, and the decoder only needs 30 digits, and we're gonna see that and verify that that's true, but the decoder only needs 30 digits to reconstruct these images, which is actually pretty cool. We have a model, and then just with 30 numbers we can generate something that is blurry but looks similar to the original. And yeah, so let's code again. Let's see, slides out. All right, let's see what this error was about. All right, when we were trying to train, we get here an error says layer sequential 11 expects 1 inputs, but it received 2 input tensors. Inputs received, blah, 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 blah. All right. All right, I think, let me take a look. Xtrain, validation data. Right, so where are we? So this is layer sequential 11. All right, so let's try to debug a bit here. So when we compile, we can add here a block. It's gonna say stacked autoencoder summary, and we're gonna run this block and we get a summary. All right, so this is the network. So this is the encoder and this is the decoder. Let's try to retrain really quickly to get the same error. And one thing I didn't do today, so we changed the runtime type. You see, this is taking a few seconds. So if we now change the runtime type to GPU, this should go faster, but we need to rerun the whole thing. So we go to run all. We're gonna have to maybe reload the dataset, define the layers, and then retrain the model. This should train fast, right? Well, more or less the same. All right, so we're getting the same error. Now we see sequential 2, and that is sequential 2. All right. If anyone can see the error, let me know. I don't see it right now. Okay. Okay, let me take a look at this. All right, let's just take a look here, just in case there's something that I'm doing differently. So stacked AE, metrics, rounded accuracy. Well, let's try to run this one just to make sure that it's not some update on the code. Right, we're gonna load this notebook. All right, so here I'm going, all right, let's terminate the other notebook here and quickly run this one. All right, we load the dependencies. All right, we run that one and we're gonna load the data set. Let's see if we get the same error. I don't expect it to be that way, but all right, so code is good here. Right, let's put them side by side just to see what we've done wrong. I'll hide myself for a bit. So stacked encoder, input shape, flatten, dense, celu, that should be okay. Keras models, sequential, celu, input shape, everything seems good. Rounded history. Oh, right. Okay. Cool. Yeah, so this might be an error. So this might be like a typo on the book. Happily, I didn't make any mistakes. I actually just copied verbatim. So this should be parentheses and we're using brackets. And if we take a look at this slide, it's actually brackets here. I'm not sure if that's with the old TensorFlow or something that used to work, but that seems to be the error that we have in our code, which is effectively the same, but there was that difference there. So we are going now to get it back here. All right, so let's try. We just put here a bracket and a bracket and run that training. Oh, manage sessions. We're going to terminate that one. I don't know if this is a current limitation, but with Google Colab Pro, I think you can run multiple sessions. All right. Okay, we're gonna run all, and this is GPU. Yeah. So this is running everything again, and once we download the data set and define everything, now we're gonna start running. We can probably use the custom the other code. All right, so this is now training. So let's see if this works properly now. Hopefully. All right, yeah, so we're training. That's good. Let's actually copy this code for rounded accuracy. Y true, Y prediction. And this is to define a custom metric. So so really quick, how to define a custom metric in TensorFlow. So we're gonna define a metric that is called rounded accuracy, and we'll get the Y true. So this would be the ground truth, and this would be the prediction. And then here we return Keras metrics binary accuracy, and we do TF round, Y true, TF round, Y prediction. And we define, so we run this block, we define this metric, and we add that to our metrics array here. So rounded accuracy, I think that's what we need to do, rounded accuracy, and that function will run on every epoch. Right now you can see the code there, so we're gonna run the code again, and we'll copy this block just to make sure we can compare the two different data sets. Right now we have this new rounded accuracy. Here is a validation loss, and now we have the rounded accuracy. And we didn't really have that here. I guess we could put like accuracy here as metric. So like something like this probably works for the default metric. Let's try that out. Maybe let's put for these tests less epochs. So we're in epoch 8. Wow, let's leave it. All right. Awesome. So let's run it again just for 3 epochs. Now we have the accuracy and the rounded accuracy. And I don't know what that means. So why these two are different. All right, so we're gonna train and we're gonna remove this one from here, and we have the train model, so we're gonna define it again. So we start from scratch. We're gonna remove this block, and then now here we can use this reconstruction function to reconstruct some images. So model X images, blah blah blah, X valid. So we have our model. So we send the model stacked AE and X valid. All right. So let's see. So def show reconstructions. We pass a model. We pass the images, which is going to be X valid. And we have the number of images. Let's say 5 as the example. And then we do some stuff here. So reconstructions are made with the model, predict, images, and we're getting and images from here, the first ones. Let's print that, reconstructions shape. And then we'll here call this reconstructions show reconstructions with our stacked autoencoder. All right, so we get 5 28 by 28 pixel images, and save fig reconstruction plot, save figure reconstruction plot. I don't know what this save fig is, but save fig autoencoders. Okay, that might be a helper function we don't need to use today. So we have the reconstructions, and here we just this block of code to make a plot of it. I'm not gonna go through it right now. And if we run that, PLT is not defined, of course. Import, so from matplotlib by plot import PLT, right? Right here. And now we can print the plot image. All right, we have many helper functions here. Plot image. All right, now cool. Okay, so I guess we can what is it? Right, so we're predicting for other images. Great. And how can we get the output? So model predict, let's see, can I get get sequential layer output. Right, so I want to get to the codings, right? So we have the we have this diagram here in which we saw how the let me see a second. Yeah, in which we saw that the codings are the output of the encoder and the input of the decoder, right? So what we want to get to now is to see if we can get the output of that layer, which in our summary appears as sequential, right? We can sequential Keras model, Keras sequential layer name. All right, we can actually name the layers. Layer 1, layer 2. All right, so we can print here not only the summary, but we can also print the stacked autoencoder layers. Let's see. Yeah, so we have two sequential models. They don't have names, so I'm not sure. Okay. Sequential. Yeah, so we don't really have names on our layers. We will have to see how to do that. You can easily get the outputs of any layer by using model layers index.output. Created by layer dense 1, which it's this one. This is dense 0 and this is dense 1. If we put a name here, let's see, so here 30 units. Okay, 30 units dense. I don't know, let's just name that this way, and then we run all. It's not a valid scope name. All right, 30 units dense. Okay, that seems fair. All right, so now 30 units dense. So now we have the output, the output of this layer, but I would like to see it. Let's see. So I'm trying to see right now. Let me see if I can explain what I'm trying to do, if you haven't realized. This network right now has a stacked encoder and a decoder, right? And has these layers and then these layers. So an input goes through this layer and this one, and then this one, and this one, and this one. We input a 28 pixel image, we get out a 28 pixel image, right? And that's what's happening here. Input, output, input, output. And that's this architecture, right? We input and we output, and the input and output are the same shape. It's 784 units, and if we reshape to 2828, it's an image. What I want to do is input an image and then get maybe these 100 units and these 30 units. This is the hidden layer I want to get, because in the output of this layer we have the codings, right? This is the reconstructed image. And that's what I'm trying to see, if there's an easy way to see to get the output. Predict layers. Layer weights. Can we get the weights? Model. Where is the model defined? Model. I don't really know how this function knows what model to use for prediction. That's really weird. Okay, so is that... Oh, okay, we're passing. It's late here. All right, so let's see layers, weights. So what would this be to train? Are these decodings? So this would be 30 units dense. So this is 1, 2, 3, 4. So it's 3. All right, so this is 30 numbers. Maybe shape. All right, so 30 units. Let's see if we get a different set of numbers every time. So here we have for image, in an image, reconstructions. Okay, so here reconstructions, image index, layers. Well, first let's see if that's something we can access. And maybe we don't need 15 images. We just need 2, 3. Right, let's see the shape of this. Let's put this here. 28 by 28. All right. All right, so we're getting the outputs, not the weight. Okay, so okay, all right. So let's try to do one thing by hand. So if we do stacked autoencoder predict, and then we get the first image. So here images, predict on images. This is x valid 0, and we just print that. We get 1. All right, so we get the output, which is an image, really. We could do plot image, maybe. No image. All right, so this way we're predicting and getting 1 image. So we can do this with maybe image 1 and 2, maybe. See, so this is the image, the first one and the second one, and no image there, right? All right, so we're getting this with these 2 images, and what I'm trying to prove here is if I do here autoencode autoencoder, and we copy the code from here. So layer 0 shape. Well, we're gonna have this shape, of course, but I want to see if I can get the actual thing. So this is here, and then this is here. Right, so these weights don't really seem to change according to the input that I'm passing through it. So this is not it. This is just the weights of the layers. But what we want to get really is the output of a different layer. Feature extractor. Okay, so we have our model, and this is what we want. So we want to extract the features of each of the layers. We're gonna take a screenshot of this. And below we have what we actually wanted, which is extracting from just one layer. All right, so great, cool. So we're gonna save this one and this one. Great, so this is what we want actually. So we want get layer, so feature extractor, the Keras model, so initial model inputs and outputs, initial model. Oh, okay, that's pretty cool. I see. This makes sense. So we're gonna build a feature extractor. So we're gonna put this sort of side by side, and here and in here. So let's build it here. So we want a feature extractor, and it's also going to be a TensorFlow Keras model, but not sequential. Now we're just going to input here our inputs and our outputs, and we'll call a feature extractor on a test input or input image. All right, so so here we do our stacked autoencoder inputs, and here we do the stacked autoencoder get layer by name, and it was, I think we have that somewhere, 30 units dense. Yeah, exactly what I put in there. 30 units dense. And once, let's see, once we have this, I'm not sure. Okay, so once we have this, we need to get here the output. All right, so let's test this out. Let's see Let's see if this does something. There's an error. There no such layer 30 units dense. All right, let's take a look. 30 units dense. All right, let's take a look at the API. So get layer. Keras model get layer. Index none. All right, so index should be 1 or well 0. So we can get by index. So 0. Maybe that works. Graph disconnected. Cannot obtain value for tensor keras tensor flatten 3 input name description created by layer at layer the following purposes were accessed without issue. All right, let's see what happens here. So Mamadou Kali, hi, nice to see you connecting back. All right, we're trying to create a feature extractor. So we have here a sequential model, and what's failing is failing. Graph disconnected, value for tensor. All right, so here we do have our model, so sequential 5, yeah, that's the one that we want. And can we get the output? Keras tensor. Outputs stacked autoencoder, get layer index 0. Keras model. Graph disconnected. Cannot obtain value for tensor Keras tensor. Name flatten 3 input. All right, so let's do a bit of cleanup. So I'm gonna let's see what we do here. Let's try to redefine this as one single. encoder, decoder. Right, so this would be, let's run this block. So this would be stacked autoencoder inputs, stacked autoencoder get layer by index. So this would be 0, 1, 2 output. And this will fail the same way or not. All right, so that seems like it worked. Run again. Awesome. So feature extractor summary. Awesome. So this is 30 units dense. And, you know, we've trained the entire model, but this is a sub model that just gives us, for each input, it just gives us the units dense. And so I guess we could get this is the decoder, right? So we define that as the decoder, and then we define an encoder. Hi, Junes Mansouri. Nice to see you connecting. All right. This book is the hands-on machine learning with scikit-learn, Keras, and TensorFlow book, Concepts, Tools, and Techniques to Build Intelligent System by Aurélien Geron. I don't know how you pronounce that properly. And it contains, you know, it says powered by Jupyter. It contains a bunch of examples, and it's updated for TensorFlow 2. You know, these things move really fast, so it's not the super current, but it's TensorFlow 2. There's a short URL you can access to see the book on Amazon. Here is an affiliate link, and you also have it on the YouTube comments chat. And you know, we've been going through this example in chapter 17 on how to build a stacked autoencoder with this code here, understanding a bit of the logic behind. And next, I'd like to do the you know, like a dimensionality reduction with TSNE, but we're not going to have time today. So yeah, I hope that answered your question. So now we were doing a feature extractor encoder. So this is the encoder. We're encoding into 30 digits each image, and the one thing that we could do is here test it. So if we give an image here x valid, and we give the first image here, yeah, nice. So we're getting the corresponding values for the first image, and if we do this, we'll get it for the second, I think. So yeah, and the encodings are different, which is pretty cool. Nice. All right, and now here we will have and we can get the encodings for 2 images like this, just with one call. And so this would be not the encoded, but like codings. We see this here, and now we're gonna build a decoder. So we will get here get layer. The input is going to be get layer indexed 3, and the outputs are going to be stacked autoencoder outputs. Hopefully that works. Input tensor to a functional must come from t-square as the input. Oh, okay. Graph disconnected. All right, so let's just say 0, 1, 2, 3, 4, 5. Okay, so that's number 5, and we'll just get the same code as in here with index 5. Graph disconnected. Maybe 4. Graph disconnected. Can obtain value for tensor keras tensor. Three, 5, 3 and 5. Tensor of a functional model inputs must come from their input. Oh, okay. So the input actually 0, 1, 2, 3. So this is index 2, which is 0, 1, 2. Functional model inputs come from TFCAR's input. They cannot be the output of a previous non-input layer. Jones Mansouri, awesome that YouTube recommended the channel to you. How did that happen? How did you get recommended this live stream or something? I would be really interested on knowing how that happened. But glad that you found me, or you found us. I will let you know, if you go to Nono.MA/Discord, you can join the live stream server. So there's like an invite to the Discord server, and yeah, there you can keep up to date with all the updates and everything that happens there. Okay, this doesn't seem as easy as I thought. Let's see if this works. Okay, so this one worked magically, which is we get the inputs and then we get the output here. Input shape. Oh, okay, so this doesn't really need to be here, I think. Maybe that's the error. Okay. Cool, so we got the codings, we got this. Awesome. Now, well, I think this one doesn't complain. Let me see. Wait. So input is 0, 1, 2, 3, 4, 5. Okay. And let me see. So functional mode inputs must come from blah blah blah. They cannot be the output of a previous non-input layer. All right. Cool. So so one thing that we could definitely do is retrain just our decoder from up there, so we can get the X train codings would be, yeah, I don't know how we would do this. Well, we could get, so feature structure encoder, we can pass all our X valid images, and then we'll get 5,000 outputs with the 30 encoding of the images. So that's good. We have this part of the graph, right? So we're getting an input here, hidden layer, and then we're getting these codings, which is good. So we got the output. We're extracting features from the model. What I would like to do now is make another network that you just give it an input here and then get an output layer there. And that seems to be already what we have in here. So the stack encoder, we could do this, probably not right now. Let's see. Oh, sorry, decoder. All right, so that works. So here we're getting images. This is not trained, but we're getting images. Maybe let's get just one. Cool. I don't know what that is, but yeah, so this is a decoder which is not trained, so we will probably have to train the decoder. So decode obtained codings with a non-trained decoder. All right, so we've defined an encoder, defined a decoder, defined, so combine them as or like stack them as an autoencoder, and then created a feature extractor, extracted codings from images, and then pass the codings via the decoder. And that has given us encoder. Extracting codings is encoding, right? And passing the codings and generating a new image is basically decoding. And yeah, so that was it. That was it for today. I have learned a lot. I hope that was useful for you. I would encourage you to like the video if you want to support the channel, and subscribe if you're new or if you're not subscribed yet, because you'll get notified when I go live next or when I upload new videos. Join the community again at Nono.MA/Discord. And yeah, thanks so much for watching, and we'll see you next time. Thanks, bye. And a quick reminder is that I don't think we're gonna have a live stream next week, but if we don't, we can, we'll have it the week after or something. Feel free to write on the chat if you want to say something before I go, if you have any questions or just want to share what you thought of today, and if you would enjoy seeing content similar to what I went through today. This book here is heavy. It's 700, 800, more than 820 pages. So I think that we have a lot to cover here. We could spend an hour and something going through 1.5 pages or 3 pages. So imagine how much we have to learn. I see Jose here is saying amazing job. I don't know who you are. Do I know you? But thanks so much for being there, for your comment, and I'm glad that you found the channel. Again, thanks everyone. I will see you next time. Bye.